In this example, let's say you have a large, heavy object, let's say a dresser or some piece of furniture or something, and you don't like it here, so you're trying to knock it over. So let's say you just stand here and start pushing on it with the intention to tip the whole thing over. Which means, what has to be true about this situation in order for the object to start tipping?
There has to be a net torque.
Right. If we want this to start tipping, we need a torque. We need specifically, we need the net torque to be some value that is not just zero. So we need a non-zero net torque. And since zero is sort of the edge case, if we have anything more than zero, it will start tipping. It's often useful to look at what would have to be true to make the net force exactly zero, and then say, we just need a little bit more than that. So let's figure out how to make net torque exactly zero. Because if we can figure out how to make the net torque exactly zero, that is how much force you have to push with to make the net torque exactly zero, then any more push than that will allow this to tip over. So let's start analyzing the forces and see if we can use those to figure out the torques. To put it another way, we can think of this also as if you're pushing just hard enough to just hold it in place, like any more and it's going to tip over, you're just pushing just barely hard enough to hold it in place. If we're considering just this box, so let's say we're looking at an extended free body diagram of just the box. And we want to consider all the forces acting on it. What forces should we include?
Gravity, normal, and friction.
We're definitely going to have force of gravity. Where should we locate the force of gravity?
At the center of mass.
Right.
In the middle.
And assuming this is uniformly distributed density, we can assume that the center of mass is the geometric center of the object. So 0.5 meter from either side, 1 meter above the bottom or 1 meter below the top. So center of mass and a force of gravity pointing straight down. And how strong would you expect that force to be?
800 newtons.
800 newtons, assuming gravity is approximately 10. 80 kilograms times approximately 10 meters per second squared is about 800 newtons. So we've got the force of gravity. What other forces should we expect to be acting on it here?
Friction and normal.
Yeah, we know there's, and how do we know those are present? How do we know there's a normal force?
Because it's not translating up, it's not moving anywhere.
Yeah, there's no vertical motion.
The y direction.
Like if this was the only force, what would we expect the object to do?
Free fall.
Right, and this is definitely not in free fall. In fact, it's not moving downward at all. Its vertical velocity is zero and stays zero. So the important thing is there's no vertical acceleration. The y component of acceleration is zero. So that means the sum of the forces in the y direction must be zero. There's a downwards component from the force of gravity, so there must also be an upwards component from the force of friction. Or sorry, from the normal force. Where should we put that? Where on the object is the normal force acting on it?
At the bottom, at the contact, probably to the right of gravity.
Yeah, because if this was just resting on the floor, I'd expect the normal force to be sort of uniformly distributed throughout the surface, the bottom surface, so probably in the center. But if you're starting to tip it over, if you tip this over just a little bit, like let's say you just start tipping it over, what's the only point of the box that is still in contact with the floor?
That point to the right where the normal force would act?
Right. If you consider the box to be very slightly tipping, I'm going to exaggerate this a little bit, but once this starts tipping, the only point still in contact with the floor is this bottom right corner. And any contact force, any force that requires the objects to be physically touching, can only interact at the point of contact, at the point where the surfaces are actually touching each other. So any force from the floor on the box, such as the normal force and the friction force, can only interact at that one location. So for purposes of trying to tip it over, we should expect the normal force and the friction force to be at this location. So we've got a normal force straight up. And how strong should we expect that to be, or do we know yet?
800.
And why would that be 800 newtons?
Because it's not moving. So those are the only forces with Y components, so they have to cancel each other out.
Right. In this particular case, these are the only forces we should expect to have Y components. If there were other forces with Y components, we need to be a little more careful about it. For example, let's say you were pushing on a diagonal. If you're pushing forward and down or forward and up, in that case, your force of your push would also have a vertical component. So that would need to be included in the Newton's first law, sum of the forces in the Y direction equals 0. But if the normal force and force of gravity are the only forces with Y components, we have the Y component of gravity plus the Y component of the normal force is 0. We already know gravity's Y component is negative 800 plus blank equals 0. That blank can only be positive 800. So the normal force is exactly 800 newtons straight up. Any questions on those forces so far? And are there any other forces we need to include?
Friction.
There's probably going to be friction, but I would not put that in just yet because friction is generally there to counteract something else. So I would usually fill in friction after figuring out what friction is acting against. And why is there friction?
The push.
Yeah, we've got this force of the push. You're standing here pushing on the box at the 1.5 meter high mark. And note that that is also a contact force. The force of the push is a force that requires physical contact. So that can only be located at the single point where you're pushing on the box. So we've got this force of the push. And we don't know how strong that is. We're trying to figure out how strong does that need to be to make this just barely start tipping over. So we'll leave that as an unknown. And then friction is presumably acting against that. And where would you expect friction to be located?
The bottom right, pointing left.
Yeah, at the bottom right, pointing to the left. And we don't know how strong that is either, but presumably it's going to be exactly the opposite of the force of the push, because those are the only forces with X components. And if we assume this is staying still, then the X components also add up to 0. Any questions on that so far? So it looks like we know the forces add up to 0 in both the X direction and the Y direction. The sum of the X components of forces add up to 0 because there's no acceleration in the X direction. That essentially just tells us that the force of the push and the friction force have to be exact opposites. Also, the sum of the forces in the Y direction add up to 0. That tells us that the normal force and the gravity force add up to 0, which is how we know the normal force is 800 newtons. But in order to figure out the unknown here, the unknown force of the push and the force of the friction, which is the same value, we need one more piece of information. What else are we expecting to add up to 0 here?
The torques.
Yeah, we should expect the torques to add up to 0. And again, we're looking for the borderline, the edge case here. We want to know how much force do you have to push with to make the torques just barely 0. That way, anything more than that, and the box will start tipping over. So let's assume that the sum of the torques adds up to 0 vector. No torque at all in total. And of course, for torque, we're going to have to choose a pivot point because torque is always defined in terms of some pivot point. If you could choose any location on this box to use as a pivot point, what do you think would probably be the easiest point to use as the pivot?
Right-hand corner of the box.
Sorry, what was that?
The right-hand corner of the box.
Yeah, if we use that corner of the box, this is probably going to make the most sense to use as the pivot point. For a couple of reasons. First of all, if this box does start tipping over, what's important about this point?
It's going to be the last thing with contact.
Yeah, once this starts tipping, this is the only point that stays in contact with the floor. This point is staying perfectly still. Everything else is rotating around that point. So every other piece of the box is moving except for this one point. So if something is rotating, the one point that's staying still, the point that everything's rotating around, is usually best to treat as the pivot point. If the object is not rotating, it's often a good idea to ask yourself, if this did start rotating, what point would it rotate around? But even more importantly for the equations we're setting up, what do you know about any torque caused by the forces at the pivot point?
0.
Right. If we choose this point to be the pivot point, any forces at that location cause 0 torque. Because we generally think of magnitude of torque as radius times force times sine of the angle between them. If you're at the pivot point, what's the radius?
0.
Right. And then if you're at the location where radius is 0, because radius is measured from the pivot point to the location of the force. If the force is at the pivot point, radius is 0, so torque from that force would also be 0. So the friction force and the normal force exert 0 torque, which is going to make our torque equation much simpler. Instead of having torques from 4 different forces, we only have to worry about torques from 2 of the forces. The other ones don't provide any torque, which makes the equation simpler and also has one less unknown, because if we have some unknown forces at the pivot point, we don't need to worry about them in the torque equation. And ideally, we want to have as few unknowns as possible. So that means our torque equation is just going to be the torque from the push and the torque from gravity. And we should consider direction just to be on the safe side here. I mean, presumably these are adding up to 0, so they've got to be opposite direction and equal magnitude. So just to be on the safe side, how do you calculate or how do you determine the direction of a torque?
The right-hand rule?
Yeah, the right-hand rule, which takes into consideration the radius, the moment arm, and the force. For instance, for gravity, if we draw in the moment arm, that'll be this diagonal here. If you apply the right-hand rule, putting your hand at the pivot point, actually, before we even apply the right-hand rule, we've got a radius that's this diagonal and a force that is straight down. The torque has to be perpendicular to both the radius and the force. What are the only possible directions perpendicular to both of these? If you could draw in another pair of directions that's perpendicular to this direction and perpendicular to this direction, what are the only directions perpendicular to both of those? Yeah, into and out of the page, or in this case, into and out of the marker board. So into the marker board, straight away from the viewer, or out of the marker board, straight towards the viewer. In this particular case, those are the only possible directions that are perpendicular to the radius and the force. So before you even use the right-hand rule, you can always narrow down the torque to 2 possible directions. It's not always going to be outwards and inwards. It's going to be whatever direction is perpendicular to both the radius and the force. In this case, the radius and the force are both part of the plane of the marker board, so the torque has to be perpendicular to that plane. But it doesn't always have to be the plane of the marker board. For instance, let's say you have a door that you're opening. If this is the door, so I'm pushing on it, let's say this is the hinge, and I'm pushing on it here. The radius would be this direction, the force would be this direction. What possible directions are perpendicular to the radius and the force? That is, if we've got radius this way and force this way. What would be perpendicular to both of those vectors? Kind of hard to see them with the hand in the way. But if you've got a radius this way, yeah, radius this way, force this way, the only perpendiculars to both of those are straight up and straight down, because this radius vector and this force vector form this horizontal plane. The only perpendiculars to a horizontal plane would be straight up and straight down. So if you've got a door arranged like this and you're pushing on it this way, the torque has to be either straight up or straight down. And you can determine which one by the right hand rule. Put your hand at the pivot point, the hinges the door is rotating around, stretch out towards the location of the force, curl your fingers in the direction the force is pointing. Now my thumb's pointing down. So trying to open the door like this would be a downwards torque. That doesn't mean anything is moving downwards, it just means the axis that the door is rotating around. So the direction of a torque is really talking about an axis of rotation, or at least a possible axis of rotation that this torque is trying to make it rotate around. For example, in this case, the torque being outwards or inwards means the box is rotating or could be rotating around an outwards-inwards axis. So rotating like this or like this. And to determine which one it is, we use the right-hand rule. But I would always recommend choosing a pair of possible directions first, using the idea that torque must be perpendicular to the radius vector, the moment arm, and torque must be perpendicular to the force that creates it. You can use these facts to narrow it down to two possible directions for torque before you even use the right-hand rule. And then use the right-hand rule to choose one of those two. So in this case, you could, for instance, put your hand at the pivot point, stretch out your fingers straight along the radius vector towards the location of the force. And note that I can still swivel my hand around, but I want to be able to swivel it so I can curl my fingers in the direction of the force, which is downwards here. So stretch out your fingers straight along the radius vector, pivot so you can curl your fingers in the direction of the force. Now my thumb is pointing outwards. So that suggests gravity is an outwards torque, which we would typically draw as a circle with a dot representing an arrowhead pointing straight towards the viewer. As for the push, if we draw this radius vector, again, the only possibilities in this case are straight out or straight in. Put your hand at the pivot point, stretch out towards the location of the force, swivel until you can curl in the direction of the force, and now my thumb's pointing inwards. So torque from the push is in the inwards direction. That confirms that these are indeed in opposite directions, so they at least have a chance of canceling out. But in order to cancel out, their directions have to be opposites. And what can we say about their magnitudes?
Same.
Yeah, they've got to be the same magnitude. So you could write this as magnitude of torque from the push equals magnitude of torque from gravity. Or more formally, you could write out their z components, their component outwards or inwards, treating, let's say, outwards as positive and inwards as negative. Well, let's go the other way around. Let's treat inwards as positive and outwards as negative. So we've got some positive value plus some negative value adding up to 0. And that works out to the same thing as they must have the same absolute value anyway. To calculate this though, how can you calculate a torque? What's a formula for torque we could use here?
RF sine theta.
Yeah, you could use radius, that is moment arm, times force, times sine theta. So for instance, we could measure the diagonal distance from the corner to the center, multiply that by the force, and then find the angle between them and multiply by that as well. And likewise, we could find this diagonal distance from the corner to this point, partway up the other side, figure out this angle and multiply this distance times this force times sine of this angle. The problem is that's going to be a lot of extra trouble. We're going to need a lot of extra trigonometry to figure out this angle and the diagonal distances. Yeah, I think our perpendicular is going to be a lot more useful here. Because you can also say, if you combine r times sine theta, that's the same as the perpendicular component of r times f. Or alternatively, you could leave r as it is and combine f times sine theta to get just the perpendicular component of f. So all of these are the same formula. They're just different ways of combining the geometry, because r sine theta is r perpendicular and f sine theta is f perpendicular. So this is just three different ways of writing the exact same formula. And I think this one is going to be a lot more useful in this case because we know the force, or at least we know the 800 Newton force, and we know the force of the push is what we're trying to find. So all of the F values are either a value we know or a value that's exactly what we're trying to find. The R values as they are would be inconvenient to use because they're these diagonal distances we don't already know. And sine theta would be inconvenient to use because it's these weird angles we don't already know. But the R perpendiculars are going to be much easier to use here. Let me draw that out separately just to figure things out. We've got this rectangular shape. We have a force at the center. We've got a radius vector. But we don't care about the whole radius. We just want R perpendicular. That is, we want to split up R into a parallel component and perpendicular component. In particular, parallel and perpendicular to what?
Would it be the horizontal?
Well, not always. In this case, yes, it will be horizontal and vertical. But yeah, more specifically to the force. We want to split up the radius vector into a component parallel to the force and a component perpendicular to the force. That's the R parallel and R perpendicular that we're talking about here. So we're splitting up the radius, not necessarily into conventional XY components, but into some coordinate system, some new axis with an axis parallel to the force and an axis perpendicular to the force. So we're measuring the perpendicular component. That's all that really matters for torque. And this is much easier geometrically because the perpendicular component of the radius, how long is that distance? What is that perpendicular?
5.
Yeah, that's just 0.5 meters. Because we know the full width of the rectangle is 1 meter. The perpendicular component of the radius from the pivot point to a spot directly under the center is exactly 0.5 meter. So that's much easier to deal with than trying to measure the distance and the angle. Instead, we can just take the perpendicular component. And note that this is exactly the same as R sine theta anyway. If we treat this angle as theta, R sine theta would be hypotenuse times opposite over hypotenuse, since sine theta is opposite over hypotenuse. So R sine theta tells you the opposite side anyway. Instead of finding R and finding sine theta and multiplying R times sine theta, we can just say R sine theta will be the opposite side, which is 0.5 meters. Another way to think about this, by the way, that's sometimes easier to visualize, you can think of the force as defining a line. The force is in some direction. If you extend that force vector far to that direction and the exact opposite direction, so keep that direction going and in the opposite direction, this line defined by the force vector is often called the line of action. I think this is terminology used more in engineering than physics, but the same principle still applies. The line of action defined by the force gives you a much easier idea of finding the perpendicular component of R. Because now we just need to measure not the diagonal distance, but just the distance from the pivot point to the closest point on the line of action. That's R perpendicular. So often a much easier way to visualize the perpendicular component of R, the R perp in the torque equals R perp times F, is just the shortest distance, the perpendicular distance from the pivot point to the line of action defined by the force. That's the perpendicular component of the diagonal radius vector. In either case, we end up with 0.5 meters. Any questions on that visualization so far? So that gives us our radius for gravity. Torque of gravity is going to be that perpendicular radius, 0.5 meters, times the force, 800 newtons. So R perpendicular times F would be 400 Newton meters. And we'll treat that as the negative direction. On the other hand, for the push, we know the force is unknown. But for the radius, once again, it would be a good idea to use just the perpendicular component of the radius rather than messing around with the diagonal distance and the sine of the angle. If we try this line of action approach, keeping the same pivot point, but we're now talking about a force located 3/4 of the way up at the 1.5 meter mark. We've got some unknown force of the push. We've got a radius vector, a moment arm, that is this diagonal that we'd have to find separately using the Pythagorean theorem. But instead of finding the radius and the angle, let's use this line of action approach. The force of the push defines a line, an entire axis. So what sort of distance are we looking for from the pivot point if we want to find R perpendicular?
The distance straight up to the force, the 1.5 meters.
If we go straight up, because the radius vector is this, but the perpendicular component R perp is the straight line distance perpendicular to the line of action. From the pivot point straight to the line of action, the shortest distance between those. And that'll of course be a perpendicular, because a perpendicular gets you the shortest distance from a point to a line. And note that that's also the component of the radius vector that's perpendicular to the force. If you think of splitting the radius vector into a parallel component and a perpendicular component, this vertical is the perpendicular component here. But it's often very useful to visualize it as the shortest distance from the pivot point to the entire line of action defined by the force. And in this case, what is that distance?
1.5.
Yeah, 1.5 meters, because that's the height above the floor where you're applying that force. So we can treat that as the R perpendicular, the perpendicular component of the radius. 1.5 meters times this unknown force of the push. So we end up with positive 1.5 meters times force of the push minus 400 Newton meters equals 0. And how would we solve that for force of the push?
Divide positive 400 by 1.5.
Yeah, add 400 to both sides, divide by 1.5. So positive 400 Newton meters divided by 1.5 meters. Meters cancel out, leaving just newtons, which is what we should expect. Dividing by 3/2 is the same as multiplying by 2/3. So that's going to be 33-ish times 8-ish, so 200, about 263, I think. Plus a little more, maybe 264. Anyone want to double check the arithmetic there?
267.
267, a little bit more than that. Thank you. So about 267 newtons. If you push with, and that's rounded up a little bit, right?
Yeah, it's like 266.6 repeating.
Yeah, so 266 and 2/3 newtons. So if you push with exactly this much force, what's going to happen?
It won't move, but if you push with any more, it will.
Exactly. This is the limit. If you push with this much force or less, you're not creating enough extra torque to make it tip over. But if you push with just barely more than this much torque, or this much force, I should say, you're creating a non-zero torque, which makes it tip over. Or I should say, it makes it start to tip over. Torque doesn't cause rotation. Torque causes a change in rotation. So anything more than this much force, and you're creating a non-zero torque, which means this is going to change from not rotating to rotating. You'd be causing a change to the rotational momentum.
So this also means that friction is 267-ish newtons, right?
Yes, exactly. The important thing about having the forces balance out as well means the force of friction has to match your force of the push. So the force of friction would have to be also 266 2/3 newtons, because if the friction wasn't strong enough, like let's say this is on a smooth surface and the friction can't match the 266 2/3 newtons. In that case, what would you expect to happen? Think about this conceptually. If this is on a smooth surface and you push it, what would you expect to happen?
It's going to slide.
Yeah, it's going to start sliding. Because in that case, if we go back to the physics of it, you're applying a force to the right. If friction is not applying enough force to the left to cancel that out, that means that there is a non-zero total force. The total force is to the right, so the object is going to start translationally accelerating to the right. It might also start to tip over at the same time. It could be sliding and tipping over. To figure out the exact balance of that, whether it's just sliding or sliding and tipping, we would need to use some more detail about that. At that point, it's no longer a statics problem, it's a dynamics problem, and gets more complicated. But you'd still start by analyzing all the forces acting on it, all the torques, figure out, do they add up to zero? Do they add up to some sort of mass times acceleration instead? Any other questions on that one?
So if you were given like the force of the push, and then they asked, is this enough to actually tip the box over, would you go through the same process? And then depending on if the force value you were given was below or above this number you found, could you then answer like yes or no?
Yeah, one way to do it would be to ignore the force that's provided and just go through this analysis and find how much force is needed, and then check, is the force provided enough to overcome this? Or alternatively, if you know how much force is provided, instead of trying to solve for an unknown force of the push, you could just fill in force of the push here and then check, does this work out to zero, or do you end up with a torque that overcomes that? Any other questions on that so far? All right, then let's take a look into angular momentum as well, because I have some questions about that. And I think it'd be good to get some of the basics out of the way now, so as to avoid more confusion later on. And I think we can get a lot of insight into rotational motion based on comparison to translational motion. For example, let's say we're looking at translational motion compared to rotational motion. For translational motion, let's say you apply a force to an object. If you just got this object, let's assume it's on wheels so we don't have to worry about friction, and you apply a force to it. You apply a force to this object, and what would you expect to happen?
Move to the right.
Sorry, what was that?
Move to the right with the slide.
Maybe it moves to the right. What if it's already in motion though? Remember, a force doesn't directly cause motion. What does a force cause? For example, let's say this box is already moving to the right and you push it to the right. Yeah, a force causes acceleration. I wouldn't really say a change in acceleration. I would just say a force causes acceleration. Force causes acceleration. The acceleration is itself a rate of change in motion. Specifically, rate of change in velocity. Acceleration equals the derivative of velocity. And those are both vectors. So the acceleration tells you how fast the velocity of the object is changing. Velocity itself being distance over time. So change in position over change in time. So velocity is change in position over change in time, and that counts as a vector. Acceleration is change in velocity over change in time, which also counts as a vector. And force causes acceleration to happen. Specifically, what equation links those together? What's the relationship between force and acceleration? Like if you apply a force to an object, it makes the object accelerate, assuming that's the only force or the total force. But what else plays a role there? They should be proportional. Like more force means more acceleration. But what's the constant in proportionality there? Yes, mass times acceleration. And it's very useful to think of mass as a difficulty level here. More mass means it takes more force to get the same acceleration. It's more difficult to change the velocity of the object. Alternatively, if we rewrite acceleration as dv dt again, so force equals mass times how fast your velocity is changing. We're assuming mass is a constant in most of these cases. We're assuming the mass of the object does not change. And a constant multiplier can be pushed into a derivative or pulled out of a derivative. So if we're taking the derivative of velocity and then multiplying by mass, that's the same as multiplying mass by velocity first, and then taking the derivative. For a constant multiplier, it doesn't matter whether it's inside the derivative or outside the derivative. For example, the derivative of 5x squared is the same as 5 times the derivative of x squared. Doesn't matter whether the times 5 is inside or outside the derivative. So we can push the mass into the derivative because we're assuming mass doesn't change as time passes. But what do we call mass times velocity?
Momentum.
Right. In other words, we can think of the force, specifically the net force acting on the object. The total force acting on the object is the rate of change of momentum. Force causes momentum to change as time passes. And the more force there is, the stronger the force is, the faster the momentum changes as time passes. So I think that's possibly one of the best ways of thinking about force, or really two ways to think about force. You can think of it as force causes acceleration, but the more massive the object is, the more force is required to make certain acceleration happen. You could also think of force as the rate of change in momentum. More force directly means momentum is changing more quickly, regardless of what the mass is. Alternatively, you could multiply both sides by dt and say force times change in time equals change in momentum. This gets back into the idea of impulse. Force times time equals change in momentum. Any questions on that so far? So let's try building this structure on momentum. Momentum, we're defining as mass times velocity. And force gives us this idea of impulse. You apply a force for some amount of time, and that causes a change to the momentum. We can do something very similar with the idea of rotational motion. What's the rotational version of torque? Did I say torque? I meant the rotational equivalent of force, which is, of course, torque. There's a lot of situations with translational versus rotational motion where there's a formula for translational motion and a formula for rotational motion that is exactly the same structure, just with different values or different meanings for the variables. And so each of the variables in terms of translational motion, there's an equivalent variable for rotational motion that means kind of the same thing, but about a spinning object rather than a moving object. So the rotational version of force, I always ask this and I always accidentally say, what's the rotational version of torque? Because I'm thinking of the answer at the same time. But the force is a translational quantity. The rotational equivalent of that is torque. A force causes a change to the translational motion. A torque causes a change to the rotational motion. Specifically, it's an off-center push that causes that rotational change. But we should be able to set up a very similar structure. You apply a force for some amount of time, that causes a change to the translational momentum. You apply a torque for some amount of time, that should cause a change to the rotational momentum, which we generally designate by a capital L. So this is the rotational version of translational momentum. Translational momentum is how fast the object is moving, including direction, times mass, which is a measure of how difficult it is to change that. Rotational momentum is changed by torque as time passes, in the same way that translational momentum is changed by force as time passes. So we still want to define rotational momentum in a similar structure here. What's the rotational version of velocity?
Angular velocity?
Yeah, the angular velocity or rotational velocity. Sometimes these are called rotational whatever or angular whatever. They basically mean the same thing, rotational impulse or angular impulse. Rotational velocity or angular velocity, usually written as the Greek letter omega. How do we define omega, the angular velocity? What does that actually mean?
How fast the angle is changing.
Sorry, what was that?
How fast the angle is changing.
Right, how fast the angle is changing. We can write that as a derivative, d theta over dt. So that's how fast the object is spinning. Angle does count as a vector here because it does have direction. It matters whether you're rotating this way or rotating this way or rotating this way or rotating this way. So angle does have a direction. You can define that using a right-hand rule. We'll get into that later. But that means that angular velocity also has a direction. It matters which direction you're spinning, as well as how fast you're spinning. So that's really what angular velocity is talking about, how fast you're spinning and around what axis of rotation. We can define rotational momentum in the same way that translational momentum is something times translational velocity. Rotational momentum is something times angular velocity. The problem is, it turns out this can't just be mass. If you look at the units of measurement here, what's angular velocity measured in? What would be the units of measurement here?
Radians?
Yeah, radians per
Time.
Yeah, radians per second usually. And radians is technically unitless. Radians is defined as a ratio of a radius of a circle versus the arc length. So a ratio of distances is technically unitless. So we usually read this as radians per second, but mathematically it's just 1 over seconds. So angular velocity is units of inverse seconds. What about torque? What units of measurement have we been using for torque? Yeah, that's measured in Newton meters. And what about time? That's seconds again. So that means in order for this to make sense, angular momentum has to be measurable in Newton meter seconds. Or if you split that out, Newtons is kilogram meters per second squared. We're multiplying it by meters and seconds. So seconds partially cancel out. Meters combined, we get kilogram meters squared per second. So angular momentum is measured in kilogram meters squared per second. What is this unit of, what does the units of measurement of this thing have to be to make this work? If we've got something times 1 over seconds and we want kilogram meters squared per second as the units, what does that something have to be? Yeah, we need kilograms times meters squared. So this multiplier here can't be just mass. It has to be something about mass, but also something about distance. And this ends up being a property that we're going to call the moment of inertia, typically written as a capital I. It's called the moment of inertia. It's also sometimes called the angular mass because it serves the same role for rotational motion that mass does for translational motion. Mass represents how much effort it takes to make it accelerate at a certain rate. Angular mass, the moment of inertia, is about how much torque it takes to make it rotationally accelerate. So more moment of inertia means it's more difficult to change the rotation, in the same way that more mass means it's more difficult to change the translational motion. So you can think of this as a level of difficulty. Moment of inertia is how difficult it is to change the rotation of an object. And in the same way that translational momentum is how fast it's moving through space, including direction, times how difficult it is to change that. Likewise, rotational momentum is also how fast it's rotating, including direction, times how difficult it is to change that rotation. So these both have the same structure. We've got something called momentum that's equal to how fast some sort of motion is happening, including direction, times a measure of how difficult it is to change that motion. Just talking about different kinds of motion. Any other questions on that so far? All right, then we'll leave it at that for now. We can take a look at the exact meanings of these variables later and try out some more examples, and I will see you next time. You're welcome.